Just 4 questions for homework class 10 on page 523. We want to go over questions 7 and 10. Number 7 says, describe how you would charge the sphere in figure 10.12 negatively by induction. Figure 10.12 was a neutral object, so it had an equal number of positives and negatives. Yesterday when I was reviewing this, I did 3 positives and 3 negatives. Today I drew 4 positives and 4 negatives. Doesn't matter, does it? Okay, I could draw 17 positives and 17 negatives. We're doing exactly the same thing. We're showing a neutral object. Okay, I want to charge this thing negatively by induction. Let's bring another object nearby, because that's what I got to do when I charge by induction, right? It's going to be positive or negative. Or do you know? Maybe we don't know. Maybe we remember from the pictures that I do in class. Maybe we don't remember from the pictures that I do in class. If we want to charge it negative, let's try bringing a negatively charged object nearby. Let's try it. Let's guess. Okay, that's going to cause the negatives in this neutral object to be pushed over to the left-hand side. Do I have a negatively charged object now? No. I've got a separation of charge, and that neutral object will be attracted to that negative object, but it's still a neutral object with a separation of charge. How do I make it permanent? Attach a ground wire. What's going to happen now? Well, those negatives that were pushed to the left-hand side are going to be pushed down into the ground. What's that going to do to my neutral object? It's going to make it positive. Did I guess right? No, I want to make it a negatively charged object. So I guessed wrong. That's okay. Some of you may just remember that when we want to charge something negatively, we bring a positively charged object nearby. If you don't remember that, that's okay. Figure it out on the fly. Bring a positively charged object nearby. Okay, the negatives are going to go to the right-hand side, leaving us with a separation of charge. We attach a ground wire. And of course, then the electrons are going to get sucked up from the ground or from whatever big object it is through the ground wire up into this neutral object. Going to get a bunch more electrons, cut the ground wire. Now we have a negatively charged object. So how do we charge a neutral object negative? Or how do we charge figure 10.12 negative? We bring a positive rod nearby, attach a ground wire, allow the negatives to flow up from the ground, and then we disconnect the ground wire before we take the negative charging object away, the positive charging object away. Is that okay? And what was the other one? Number 9 we need to go over? Compare the distribution of charge on a hanging aluminum and glass rods if both are touched at one end by a negatively charged ebonite rod. That's a good question. That's a good question. Let's draw a picture. We have an aluminum rod. It's hanging, so assuming it's not grounded here. Both are touched at one end by a negatively charged ebonite rod. So we're going to make our negatively charged ebonite rod, whatever ebonite is, right? Whatever that is. What's going to happen to the protons in that aluminum rod? What's going to happen to the protons there? Nothing. Right? What's going to happen to the electrons? You're going to get, for the most part, you're going to get those electrons pushed away to the left-hand side, right? So this is, sorry, no, we're not. They're touching each other, right? If they're touching each other, we get conduction. So we get a transfer of negative charge this way, leaving us with a whole bunch more negatives in there. They both become negatively charged. Are they going to balance out necessarily? Not necessarily, but we're going to get a large transfer of negative charge from the one object to the other. Make sense? Okay, that's aluminum. What about glass? How's it going to be any different? Is there a difference? Well, what's the difference between aluminum and glass? Yep. Good. Aluminum is a better conductor, a way better conductor than glass is, right? Does that mean we're not going to get any electrons transferring here? No, it doesn't mean that at all. We will get some electrons transferring there, but are we going to get as many electrons transferring as we got up here? No. So you're going to get a similar effect in both of them, but the effect will be much more magnified in the aluminum rod than it will be the glass rod. Make sense? When you rub a balloon against your hair, I mean, you've all done this, right? You rub the balloon against your hair and then you stick it against the wall. And then you watch it stick to the wall, right? Did anybody over the last few days ever think, why doesn't that balloon transfer its negative charge to the wall? They both become negative and then repel. Why does the balloon stick to the wall? And on one level, you can say the balloon is negative, the wall is neutral. They should attract each other, right? But as soon as they touch each other, shouldn't the negatives transfer and balance them out and repel each other? They don't do that. Not right away, at least. Why don't they do that right away? Because, go ahead. Well, because the wall is so much bigger, yes. They're never going to balance out, right? But why doesn't the wall just become a little bit negatively charged? Even if it becomes a little bit negatively charged, it should still repel the balloon, right? Why doesn't it? Or at least why doesn't it right away? How would it be different if you had a metal wall, and you had a metal balloon? If you had a negatively charged metal balloon and you touched it against a neutral metal wall, exactly. If you had a negatively charged metal balloon, touched it against a neutral metal wall, then charges would try to balance out very, very quickly, and they would repel each other because they both become negatively charged. When you touch a balloon against the wall, there is a force of attraction, but because they're insulators, that transfer of charge doesn't happen very efficiently, right? Because they're both insulators, which means that you got that neutral wall and it stays neutral for a while because you don't get that easy transfer of charge from the negatively charged insulating balloon to the neutral insulating wall. Is that all right? So it's kind of the same thing that's going on here, right? Conductors transfer charge better than insulators do. B, after a small negatively charged metal sphere momentarily touches a larger neutral metal sphere. We just answered that question, right? A small negatively charged metal sphere touches a larger neutral metal sphere. It doesn't really matter if it's larger or not. What's going to happen? Well, when they touch each other, because they're metal, there's going to be electrons transferring this way. That's going to make both of them negative. And as they both become negative, they're going to start repelling each other because like charges repel. So they're going to attract each other first. Negative is attracted to neutral, and then they're going to touch. They're going to transfer charge by conduction, and then they're going to repel each other. All right? There used to be a question that I gave on a test, on a unit test, that was almost exactly like that. And I can't remember if I still have it on your test for this semester or not. But whether it is or isn't, it's an important concept, right? If you do this with something that's insulating, like the balloon in the wall, you don't get that force of repulsion, at least not right away. You do that something with something that's conducting, then you do get that force of repulsion almost instantly. All right. Let's spend just a couple minutes reviewing the torsion balance experiment that we looked at yesterday. Remember how it worked? We had a string hanging from the ceiling. And that string, when we twist that string, we can measure the amount of force that was required to twist it a certain amount, a certain angle, just based on the torsional properties of the twisting properties of the string. Previous experiments would tell us that if you twist the string a certain amount, then it must have required this much force in order to do it. On the end of that string, we've got a rod, and on the end of that rod, we've got two objects. Object number one down on the left-hand side, and then we've got object number anything, something, on the right-hand side. Object number one is charged. Object number whatever on the right-hand side, whatever. Maybe it's charged, maybe it's not. Object number two is going to be brought nearby object number one. It's coming near it. That's going to cause a force of attraction or a force of repulsion. on object number 1. Doesn't matter which. That's going to cause object number 1 to be pulled towards number 2 or pushed away from number 2. That's going to cause the string to twist. Now remember, the amount the string twists tells us how much force of attraction or repulsion we had. We can measure the amount of charge that we have for charge 1, Q1 we'll call it, not really in coulombs, but we can measure it in terms of what it is compared to what it was. Okay, if it's a value of Q and I touch it against something that's neutral, it becomes a half Q. If I touch it against something that's neutral again, it becomes a quarter Q. I can change the value of Q1 or Q2 for that matter without actually knowing the value of those charges in coulombs. And finally, the value of R, the distance that separates charge 1 and charge 2. That's pretty easy to measure, right? A distance is always easy to measure. So Coulomb performs 3 different experiments. In the first experiment, he manipulates the value of Q1. He changes what Q1 is. He's got a certain value, call it Q. Then he changes it to a half Q. Then he changes it to a quarter Q, and then to an eighth Q, and so on and so on and so on. He keeps changing the value of Q1, all the while keeping the value of Q2 and R constant. They're control variables here. When he does that, he plots a graph, finds that it looks like this. That tells him the relationship between F and Q1 is a linear one. F is related, directly related to Q1. As Q1 goes up by a factor of 4, F goes up by a factor of 4. As Q1 is decreased by a factor of 12, F is decreased by a factor of 12. They're directly related to each other. Well, he performs another experiment. This time he manipulates the value of Q2, and he sees how F is affected by changing Q2. Q1 and R are control variables. It's a straight line as well. F is directly related to Q2. As Q2 goes up by a factor of 16, then F goes up by a factor of 16. Then he does one final experiment where he manipulates the value of R. Sees how F responds to that. Keeps Q1 and Q2 constant through this experiment. He plots that graph and it looks like this. That gives him a relationship that's different from the above ones. F is related this time not to Q1 or Q2 or R, but rather to the inverse of the square of R. F is inversely related to the square of R. Yesterday we talked about an inverse square relationship or an inverse square law that exists in Coulomb's law and Newton's law of universal gravitation. It's an inverse square law because the force is inversely related to the square of the distance. Now let's put all those 3 together. The electrostatic force of attraction or repulsion is related to Q1, Q2 over R squared, but it's not equal to that. It's almost equal to that, but to make it equal, we have to stick a little, what I call a fudge factor. Really, it's just a constant. We have to stick a constant in front of that. So if we stick this constant K in front of Q1, Q2 over R squared, then it's equal to the force. That value, the value of that constant, we call Coulomb's constant. It's on your data sheet, 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. What do you notice about that constant related to the constant for gravity? Remember Newton's law of universal gravitation, G m1 m2 over R squared. Equations are almost exactly the same, right? Let's sub in Q for M. Let's sub in K for G. But certainly the structure is the same. What do you notice about that constant versus this constant, G? Yep. It's way bigger. Okay, G is 6.67 times 10 to the minus 11. 10 to the minus 11 compared to 10 to the positive 9. So the electrostatic force is going to be much stronger of a force. And we talked about that yesterday, right? Why it's a stronger force and where we see it as a stronger force. This is almost always, in almost every situation, a stronger force than this force. We saw yesterday that it is a large force compared to a small force. We saw yesterday that they're both inverse square relationships because they both have F inverse related to the square of the distance. We saw yesterday that Coulomb's law can be attractive or repulsive because we have two kinds of charge. Think about that. We have positive charge and negative charge, and that can result in attraction or repulsion. Versus gravity, where we only have one direction of the force, it's attractive. Why? Because there's only one kind of mass. You don't have positive mass and negative mass. If you did, then you could have attraction and repulsion, but we don't. That's where we left off yesterday. Today we're going to start doing a problem involving Coulomb's law, a rather straightforward one involving Coulomb's law. It says a small metal sphere with a negative charge of 2.1 times 10 to the minus 6 is brought near an identical sphere with a positive charge. Even before we finish reading the first sentence, I see something that I want to circle in red, something that I want to draw attention to. A small metal sphere with a negative charge of 2.1, identical sphere with a positive charge of 1.5. Yep. Positive and negative. Okay, let's circle this and just write a little note that it's negative and positive. The distance between the centers of the sphere is 3.3 centimeters. I definitely want to circle that. Okay, I definitely want to be in meters when I'm doing these calculations. Notice my charge is in coulombs. It says 10 to the minus 2.1 times 10 to the minus 6 coulombs. They're giving us a bit of a break because a lot of times they give us a charge of 2.1 times 10 to the minus 6 coulombs. They're not going to say that. Not going to say it in that way. They're going to call it 2.1 microcoulombs, and we're going to have to remember to convert to coulombs. We want to find the magnitude and the type of force. Okay, how big is the force, and is it attraction or repulsion of one charge acting on another? All right, what do we got for givens here? We've got charge 1 is negative 2.10 times 10 to the negative 6 coulombs. We've got charge 2 is positive 1.50 times 10 to the negative 6 coulombs. We've got a distance that we're calling r as 0.0330 meters, right? 3.3 divided by 100. We want to find the force. We only have one equation that allows us to find electric force, at least right now. It's KQ1 Q2 over R squared. So let's start plugging numbers into that equation. 8.99 times 10 to the 9, the constant that's on your data sheet, times Q1 times Q2 divided by the distance squared, 0.0330 squared. Have I missed anything? Have I missed anything? Okay. It is negative 2.10, but I'll tell you what, a little bit of a trick question I just asked. It is a negative charge. One of them is a negative charge, but I'm not going to plug that sign into the equation. I haven't missed anything. It's important that one of them is negative and one of them is positive, but not mathematically. Don't ever plug a sign of a charge into any equation. There will be lots of equations that we do this year that involve charge. Don't ever plug the sign of a charge into any of them. Here's why. For us, negative and positive in equations mean direction. That's our sign convention. If we start plugging a negative in because it's a type of charge, not a direction of something, then we're going to start mixing and matching two different sign conventions with the same signs. We're going to get a negative value for force, and then we're going to think that force is to the left because it's negative. Just don't do it. Sometimes in other textbooks, some teachers even tell you, yeah, plug the sign in. If you get a negative force, then that means it's attractive. If you get a positive force, that means it's repulsive. It can work. I'm just telling you it ends up being confusing. So don't do it. There's always another way of determining the direction of the force. We don't need an equation to determine the direction. We need an equation to determine the magnitude. So just don't plug in the sign of a charge. Let's do the math here. Let's do the math, and then we'll figure out the direction some other way. We got 8.99 times 10 to the 9 times 2.1 times 10 to the minus 6 times there we go, times the 1.5 times 10 to the minus 6. Now let's press equals, and then let's divide that by 0.033 squared. And we end up getting 26 newtons. All right, good. There's the magnitude of the force. Now, is it attractive or repulsive? The equation doesn't tell us if we don't plug in the sign of the charge. How can we figure out whether it's attractive or repulsive? It's the easiest question in the world, Hugh. One's positive and one's negative. It's got to be attractive, right? Opposite charges attract. See what I mean? Some teachers will tell you, plug that negative sign in right here. Plug that in right there. I'm telling you, don't. Okay, some people will tell you to plug it in right there because the answer, the negative that you get for a force, would tell you that it's an attractive force. We don't need that. That's just going to confuse us somewhere down the road when we're talking about direction left, right, up, down. That's just going to make us think it's a downward or leftward force. It isn't necessarily. It's an attractive force, but it could very easily be a force to the right. We see a negative, we're going to automatically assume it's not to the right. Just don't plug it in. Now, one final little thing that I want to explain to you here before we go on to the problems. It says calculate the magnitude and type of the force of one charge acting on the other. If this is charge 1 and this is charge 2, understand when we calculate this force of 26 newtons, the force of charge 2 on charge 1, right? Charge 2 pulls charge 1 towards it. It's 26 newtons. The force of charge 1 on charge 2 is to the left because it's number 2 is pulled towards number 1. We'll call that F12. It's also 26 newtons, right? We're not finding the combined force. We're not finding the force on just this one. We're finding the force on both of them. If object A applies a force on object B applies an equal and opposite force on charge A. By the way, I shouldn't write down 26 newtons for this one. I should write down what? Negative. Because remember, negative means left, not attractive, for us at least. All right, is that clear? Those aren't that hard, right? Careful with the r squared. Don't forget to square that r. That's a relatively common mistake. KQ1, Q2 over r. Careful with the signs. Okay. Otherwise, should be good. Take a look at those. Take a look at that question, please, for the next couple of minutes. See what you can do, and then we'll move on to another example in a minute. All right, let's take a look at another one, page 531. It says, the two spheres in example 10.1 are momentarily brought together and then return to their original separation distance. What's the force now exerted by one charge on the other? Well, let's go back to example 10.1 for a second. The charges were 2.1, negative 2.1, and plus 1.5. Negative 2.1 times 10 to the minus 6 coulombs, and 1.5 times 10 to the minus 6 coulombs. The separation distance between them was 0.0330. How's this going to change? If I have the same charges as I had in the last question, and I have the same distance as I had in the last question, then how's the force going to change? There's got to be something here, because they're not giving me another question that's exactly the same as the first one. What's the deal here? Yeah. Yeah. When we touch them together, the charges are going to change, right? What happens? Minus 2.1 and 1.5 becomes a total charge of negative 0.6, but it splits up evenly, so it becomes negative 0.3 times 10 to the minus 6. So we're going to change that Q1 and Q2 to negative 0.3 times 10 to the minus 6 coulombs. Now you could say 3.0 times 10 to the minus 7 coulombs, but I think it's easier just to leave it as negative 0.3 times 10 to the minus 6, right? Negative 2.1 plus 1.5 divided by 2 gives me negative 0.3 times 10 to the minus 6. My distance is 0.0330 meters. We want to find the force. We're dropping the sign of the charge like we always do. Hey, look what I'm doing. What did I just do there? What did I just do? You? I squared the 0.3 times 10 to the minus 6. How come? Because it's the same value. I could have just drawn or written it out, 0.3 times 0.3, to save myself a little bit of time and a little bit of effort writing on the board. It's the same charge, so why not? Let's figure out what that value is now. We got 8.99 times 10 to the 9 times 0.3 times 10 to the minus 6 times 0.3 times 10 to the minus 6 divided by 0.033 squared, 0.74 newtons. Attractive or repulsive? It was attractive, right? Because we have a positive and a negative. Now it's repulsive because we have a negative and a negative. Remember what we said a little while ago when we were reviewing? If you have two things that attract each other, as long as they're conductors, two things that attract each other, they touch each other. If they're conductors, what's going to happen? Charge will transfer, they'll balance out, become like charges, and then repel each other. That's what's happening here. The 0.74 Newton force of repulsion on each of those charges. Let's take a look at this question, please, on page 531. The homework for tonight is worksheet number 6. Keep in mind on a few of those questions, they're just straightforward. Here's a charge, here's a charge, here's the distance. Remember unit conversions, microcoulombs, centimeters, and so on. Some of those questions, the charges touch each other, like in this example question and in this practice problem. In a few of these questions, they ask me for the acceleration of one of those charges. How do you think you might find that? How do you think you might find the acceleration? Anytime in Physics 30 you're asked to find acceleration, here's what I want you to do. It doesn't matter whether it's the context of electrostatics or magnetism or anything else. You want to find acceleration? Get the force. Okay, get the force. The force needs to be with you. Once the force is with you, then say A is equal to F over M. Literally, divide the force that you calculate by KQ1, Q2 over R squared, or by some other method later on in Physics 30, divided by the mass. That's going to give you the acceleration. Okay? Anytime you're asked a question to find acceleration, think of it as a question where you're asked to find force, and then simply divide it by mass. Okay, that's it for today. You can have a few minutes, about 5 minutes here to work on worksheet number 6, and then finish up the rest of those questions for homework tonight, please.